So this video talks about how to compare two line segments via an inequality. Okay, so the underlying assumption that we're having coming in is we're in some sort of incidence geometry. All the between us axioms are satisfied, and we also have already the three line segment congruence axioms as well as propositions 8.1 through 8.3, which deal with adding lines and subtracting lines. Okay, so in terms of the inequalities, here's how we define less than. Okay, so you start off with two line segments. We'll go ahead and grab line segment AB and CD. Then what we're going to define is we're going to define that line segment AB is less than line segment CD, and we'll use the standard notation of the less than symbol. Notice in terms of the picture, I on purpose drew these pictures so that the line segment AB visibly looks shorter than line segment CD. In other words, trying to play on your intuition right now. Okay, not play on as in make it bad, but play on as in say yes, it's going to work here. Okay. Now, here's the formal way of defining that a line is shorter than, or less than another line segment. And this definition actually still holds true in classical geometry too. We just didn't talk about it because we hand waved and said, hey, it visibly looks shorter. We're totally good. Let's go. Okay. So here's the formal way of defining a shorter line segment. So if there exists some point E, the point E has to be between the endpoints C and D of your line segment. That's going to be the longer of the two line segments. Okay. Now here's the catch on how you pick point E. Point E needs to be chosen so that line segment CE is exactly congruent to the line segment that's going to be shorter. So that's the one line segment here, AB. Now, fair warning. Well, not really a warning, just as an FYI. This here, we totally could have copied the line segment AB, not starting from the point C. We could have copied it from the other endpoint. That's totally fine too. You just have to have that the line segment E to one of the two endpoints is congruent to your other line segment AB. Okay. Now, if that line segment E exists inside of the line segment CD, this then tells you that AB is less than CD. Notice we also get the standard way of reading the inequality backwards, that line segment CD is greater than or longer than AB. Now what happens if you try to do this method, but that point E doesn't end up inside of your line segment? So suppose we have this scenario. Suppose we have line segment AB up here. And suppose our line segment CD is down here. We try to copy the line segment AB starting at C, and we go, and then when we copy it, it actually gets longer over here. Dotted lines are bad. If I had a different color that I could easily grab, I'd pull in a different color right there. In this case, because E is not inside of the line segment CD, what that then tells us is, hey, AB is not less than CD. In fact, we got a reversal, and since AB is not less than CD, instead we get the reverse, which is that AB is greater than CD in this situation. If we had actually ended up with point E and point D being the same point, then the two line segments would have been congruent. But just as a heads up, what happens if you try to copy the line segment and it doesn't work out. Okay. Now, turns out there's a couple properties associated with inequalities, and all of them are summed up in proposition 8.4 in this section of your textbook. So, in this particular proposition, there's a bunch of different things. Let's just start with the first one. So the first one says you've got some line segment AB, it's congruent to some other line segment. You've then got a second line segment CD congruent to some other line segment. Remember, the primes just mean we were too lazy to come up with new names for those letters. Then it turns out that if you already know that line segment AB is less than or shorter than line segment CD, then you'll automatically get that you can, replace AB with A prime, B prime. You could also replace CD with C prime, D prime, and you'll get the same inequality. Now, if and only if means you can go either way. So if you don't know if AB is less than CD, but you did know this inequality with the primes, you could also then read it backwards as well. In other words, algebra works. If you've got two line segments that are congruent to each other, you can replace one of the names of the line segments anywhere in any property you have with that name of the other one. Now, second main property talks about the inequality relation specifically as an order relation. Now, I am not assuming that you guys know what an order relation is, so don't worry about that naming convention. But what it means is the following. Okay? The first thing that it means is it means that if you have the line segment AB is less than line segment CD, and you also know line segment CD is less than some other line segment EF, you can link the inequalities together and get the relationship that you expected. This is, if you want the buzzword, this is known as transitivity or the transitive property. Okay. Now, that's the first thing that you need in order to be an order relation. Again, I'm not expecting you to remember or know what an order relation is. And the second criteria that you get from an order relation is actually where the name comes from, this name order, and it comes from the following property. If you have two line segments, AB and CD, you're going to get exactly one of three cases. Either AB is the shorter one, so AB is less than line segment CD, or AB is longer than CD, so AB is greater than CD, or they are congruent to each other. In other words, if you take any pair of line segments in your geometry, you will always be able to compare them. They'll either be congruent or one of the two line segments will be longer than the other one.